So we will continue with our stability analysis in this lecture. From the previous lecture we saw root locus, and then we said that root locus is plotting how the poles are changing when we increase the gain value, and then we said we were not interested in the exact Kp value, but we were interested in the qualitative understanding, and also not so rigid quantitative value, but some range of Kp wherein the system will be stable, etc. And that is what we are going to use the concept of frequency analysis into this, and then we are going to see how the frequency analysis helps in the concept of stability. And so if you can recollect from the frequency analysis presentations, so this is what we had as the summary slide from that. So when we excite system with a sinusoidal input, so the output is also sinusoidal at the steady state, and then the magnitude of output depends upon the sign of the input, the amplitude of the input, and also the magnitude of a complex number g of j omega, where g is a system, g of s is a system, and then phase, there is also a phase lag that we observed in the output. So we had the magnitude change and also the phase change. So this is what we observed, and then these formulas we gave for the amplitude and then the phase. So we also plotted the amplitude and phase with respect to the angular frequency, and we said this plot is called the Bode plot. So we are going to see how this Bode plot is going to help us with the stability analysis. So that is what the topic for this lecture. So we will also try to understand intuitively what happened in the general case, and also we will towards end of it we will try to see where it fails, where this kind of analysis fails. So again, to summarize, to tell this from the previous lecture. So we said that okay, why we are interested in the range of Kp, because the model itself, the transfer function itself is an approximation. So we are not interested in the particular value of gain at which it goes unstable, but a qualitative understanding of what value of gain the system goes unstable, etc. So that's what this will give, this analysis will give us in a better way. So now so why now we again ask, okay, this is good, when we say that when we increase the gain the poles are moving towards the right of S plane is okay, but why everything happens? Can we ask this question in a deeper sense, is something we are going to say. So this frequency analysis is helping us to give some insight, but this insight is not a very strong insight, basically because this intuition is not a straightforward intuition and can fail at sometimes, but it is okay to have this intuition to begin with. Okay, so remember this, what point we are trying to emphasize is this intuition is okay to have to begin with, but this is not a strong intuition and it can fail at times. Okay, so that is what we are going to keep this point in mind, so that we will go and we will see this where it fails, etc., but we will just have this. So why it goes unstable? So one thing we can say is okay, whenever we have a pole on the right hand side of S plane, we are going to have some positive lambda into t, and that is actually causing an increase in the amplitude, so of a sine wave or something, so that is what is going to unstable. But why this increase? So now we ask this question, why this increase in amplitude happens? So if we ask this, then there is a rule called Barkhaussen's rule. Okay, if in electronics, for creating an oscillator, etc., we use this Barkhaussen's rule. So that's what it basically says. Okay, what it basically says is Barkhaussen's rule. What it basically says is if in a system, okay, if you have a frequency for a particular frequency, if this frequency when it goes around the loop and comes back at the same point here, if it is in phase with this particular sine wave, so this is the input and let us say I got an output like this which is in phase with this, and the if the net gain of this particular wave, how much the magnitude has changed, okay, if it is greater than or equal to 1, either that it has increased in the amplitude or that it is having the same amplitude, then basically this sine wave is going to go through the loop again and again, right. So basically if it is having a let us just run through it, okay, once and then see how it goes. So basically first time let us have a sine wave is like this here, and then it goes around the loop, and then let us say now the amplitude has decreased. Let us say the amplitude is the modulus of g of j omega at that particular angular frequency, okay, at that particular angular frequency is say 0.5. So basically when it comes back it will be like and let us say this is the frequency at which it is going through the loop and coming back in phase, okay. So when if this comes in phase and it is 0.5 in magnitude, then it becomes half of this, okay, and in the third if it goes around again and comes back, it becomes like again smaller. So basically you can see here when it goes around the loop and comes down, its oscillation is going to, the amplitude is going to die down. So basically this frequency will die down as time progresses and becomes, it's a stable system. But what happens when the amplitude becomes equal to 1? When it becomes equal to 1, this again is like same sine wave, and this also is the same sine wave, everything like is in phase. So basically now what happens, the output is having a same constant amplitude, okay. So it is going to keep on oscillating with same amplitude, but still it is not going to unstable, it just keeps oscillating, the oscillation does not die down. And what happens if the gain is greater than 1? So if the gain is greater than 1, what happens, the next time it comes around loop, this is going to increase, and the next time it is going to increase more. So basically if you can plot the output, basically the amplitude gets increasing. So this is the intuition that the Barkhausen criteria gives, okay, and this intuition we are using it for our analysis for stability, okay. So Barkhausen says that it should be in phase or multiples, the phase shift caused by this loop must be multiples of 2 pi, okay, which is in phase, like, so after every 2 pi interval the sine wave is going to get phase, right. So what does that mean? Sin omega t plus some multiple of 2 pi is again going to be sin omega t. So any multiple of 2 pi is going to become the same wave again and again. So if this particular wave is going to be like when it goes around loop and comes back, if it is going to be multiple of 2 pi, the phase lag introduced by the loop is going to be multiple of 2 pi, the sine wave is going to be in phase, and if at that particular frequency if the gain is going to be greater than or equal to 1, then it's going to oscillate. If it is equal to 1, it is going to be oscillating, if it is greater than 1, it is going to be oscillating with an increasing amplitude. If it is not, if it is less than 1, then it is going to die down, the oscillations are going to die down, so it is a stable system. So that is what the Barkhausen says, and then with the Barkhausen's criteria, if we go and look at the Bode plot, let us see what happens. So this is what we saw already. So this is the summary of it. So if it is in phase or multiple of 2 pi, and then the magnitude is less than or equal to 1, that is when it is going to go to unstable domain basically. Actually equal to 1 it is still like stable, it keeps oscillating, greater than 1 it is going to be unstable, that is what we are going to see. So in our system what happens is, here we have a minus sign, okay. Here we have minus sign. So we saw in our frequency response analysis, like every minus sign is going to contribute to a minus 180 degree phase shift, right. So what we did, we did minus 1 and we saw the Bode plot etc, and then we saw it is minus 180 degree. So every minus sign is going to contribute to minus 180 degree. So this minus sign is there here because it is subtracting the output from the input. So one minus 180 degree phase shift is already there. So for a wave that comes out through the loop and crosses this and then it is going to if there is a wave here and it is coming throughout the loop and coming to the same point again, one thing is minus 180 degree is already there due to this minus sign, and then there is also a phase lag that is contributed by this system, and this phase lag is nothing but the magnitude of the amplitude of the phase lag is nothing but the angle contributed by the g of j omega, complex number g of j omega. So for some particular frequency, if this angle of g of j omega is going to be minus 180 degree again, then basically this minus 180 degree due to this particular system, and this minus 180 degree is going to get added to be minus 360 degree, which is like a multiple of 2 pi, right. So since this becomes multiple of 2 pi, this particular frequency at which the phase angle is going to be minus 180 degree, that particular frequency is of some importance, and that particular frequency we call it as a critical frequency. critical frequency in sense it's like an important of all the frequencies we look at this particular frequency, and this is of the most importance from the stability perspective, that is what we are going to say. So, if at this particular frequency, if in this frequency, if only at this particular frequency the system is going to be the sine wave is going to come in phase, right. So, at this, so Barkhausen says for such frequencies, if at that frequency the magnitude is greater than or equal to 1, then the system is going to probably go to either oscillate, the system is going to be oscillatory. If it is greater than 1, it is going to be unstable system. So, now at this particular frequency we look at the gain of the system, and if gain of the system is less than 1 at that point, then basically it means system is stable. If the gain is equal to 1, then the system is going to oscillate at this particular frequency value. If it is greater than 1, then the system is going to oscillate oscillate with increasing amplitude. So, that is what we are seen from the analysis of how this frequency interference of the frequencies happen. Okay. So, this is the idea. Okay, this is the idea of the frequency response analysis coming into the stability perspective. So, to summarize, basically what we are going to say is the summary of all these things is nothing but at the frequency where the phase shift is minus 180 degree contributed by angle of g omega. So, this is at this frequency. So, that frequency we call it as a critical frequency omega c, and what we say is if at this frequency the magnitude, which is the gain contributed by modulus of g omega, if it is greater than unity, then the system is going to get unstable. So, this particular thing is called a critical frequency. This particular frequency is called a critical frequency at which the phase lag is given by minus 180 degree. And why minus 180 degree? Because the minus sign contributes to another minus 180 degree. So, totally we get minus 360 degree, which is multiple of 2 pi. So, the Barkhausen's condition is satisfied. So, that is what we are going to remember now. So, basically here if you can do the body plot, and then we see at what phase, at what frequency is this system going to minus 180 degree phase shift. So, minus 180 degree phase shift is at this particular frequency, and this particular frequency is nothing but omega equal to 1.41 radians per second, right. So, if you can just plot here, and this is 1.41 radians per second. So, omega c value here. So, that frequency at which the phase is minus 180 degree is called the critical frequency, and that frequency in this case is 1.41 radians per second, and at this frequency we look at the amplitude, and remember this amplitude is now in body plot, it is in dB. So, basically 0 dB means gain is 1, okay, because remember dB is nothing but 20 log of the gain. So, if gain is 1, then log 1 is 0. So, that is when 0 dB comes. So, this anything which is less than 0 dB is minus. Minus in logarithmic scale is nothing but less than 1. So, if mod g is less than 1, then basically you get a minus value here. So, here it is nothing but the gain is less than 1. So, in this system when the frequency, when the system is at the critical frequency, when the phase shift is minus 180 degree, the gain is less than 1. So, the system is stable. First conclusion we can make is okay, the gain is less than 1, so that the system is stable. Now that is not the question we are going to ask. The question is like my model itself is an approximate thing. So, with this just understanding, okay, this model is stable, we cannot conclude anything. Then we ask the question like, okay, what is the gain that I can multiply to the system so that it becomes unstable. So, if I can multiply with a very high gain and then system for making the system to go unstable, then it means that I am very comfortable with the stability of system. So, if I just multiply system with, for example, let us take here, okay. So, in this case the gain margin is not okay, we say the difference between this particular value, the gain at omega c and 0 dB is nothing but 5.58 dB, okay. So, this particular value is 5.58, okay, which is nothing but 1.9, okay. Remember for the same system we have analyzed the root locus, and also we found that the ultimate gain was 1.9, that is the same thing here, okay. That is for the same thing, all the methods will give the same values, okay. That is methods may differ, but the values is the same. Okay, so you can use any method to whatever you feel comfortable to find this ultimate gain. So 5.58 dB is 1.9. Why? Because for if 20 log 1.9 is 5.58, you can check this. Okay, so basically what we are going to say is, if I multiply if they multiply the system with a gain of 1.9, then the system becomes unstable. So when I am modeling the system, if I made some mistake, say instead of taking the gain as 1.2, okay, due to some reason I took this gain as 1. So instead of getting 1.2 by s cube plus s square plus 2s plus 0.1, like I am getting a value as 1 by, I made a mistake in modeling, so I took by 1 by s cube plus s square plus 2s plus 0.1. That may be one reason. Or it's a non-linear system, so I linearized it and then I made some approximations and then I got this. Or there are a lot of approximations in modeling. So basically, considering all the approximations, I am saying I have a flexibility of making a mistake of 1.9 times the gain. Okay, so only if my mistake, if I multiply by a gain of 1.9, then the system will go unstable. So this is the bandwidth I have. Okay, so for my system to go unstable, I can give a gain of 1.9 till I multiply by 1.9 times the gain. I am not going to go to unstable. So that is what we are going to tell there. So this margin, okay, this bandwidth or this margin, we call it as a gain margin. How much gain I can multiply and still be stable. So I have a stable system. How much gain I can multiply and still be stable? So that maximum gain, it's what called the gain margin. So it is nothing but 1.9, and in decibels it's nothing but 5.58 dB. So it's actually a multiplicative gain, but when we convert into decibels, basically it's it's something like, if it is a multiplication k into g, when you take the logarithm of it, now it becomes like log k plus log g, right. So this decibels is nothing but how much gain you are going to add. So remember, when you give the gain in decibels, you are telling how much gain in decibels I can add. Okay, because when we convert into multiplication becomes plus in when we take when we take logarithm of it. So logarithmic scale, it becomes addition. Okay, that's something you can remember. But essentially all the things, all logarithm, mathematics, all these maths left, what we are asking is what is the gain I can multiply such that the system will still be stable. What is the maximum gain I can multiply, still the system will be unstable, still the system will be stable. That is what you are going to ask. So which means basically, if you multiply by kp, if you multiply by gain of 1.2, it is still stable. If you multiply by gain of 1.4, it is still stable, but if you multiply with the gain of 2, it will go unstable. So that is the gain margin. What is the margin, what is the bandwidth of gain I have, so that the system will be still stable. That is what we are going to ask. That is the question, that is the answer for gain margin. Now when I am modeling, I not only can make mistake in gains, I can also make mistakes in finding these poles and all the approximations. Even this particular term I can have some mistakes. So even the phase is a problem. So this minus 180 degree at this particular omega c may not be correct. I can probably have my actual model may go, my actual process may be having omega c of like say 1.3. I did some mistake in modeling because I did some approximation, I did something. So maybe so that this phase was something different. Okay, so now we ask the question like, okay, what is the phase difference, okay, I have to add, so that the system what is the extra phase lag that I have to introduce, so that the system will go unstable. So now, forgetting about the gain, let us say the gain is correct, let us say that the gain plot is fixed. Now I ask this question, now I assume that okay, I made some mistake in modeling, so even this phase plot is inaccurate. So like something else is going to happen, so that this phase diagram is going to change. So what is the phase change I can introduce, phase lag I can introduce, so that this system will still be stable. Similarly, like the same question we asked for gain, we are asking for phase now. Initially we fixed the phase plot and then we asked the question for gain. For given phase plot, what is the gain I can add, I can multiply, so that the system will still be stable. So the multiplicative gain when the system is stable is going to be called as a gain margin. And now I fix the gain plot, and then I ask the question, what is the phase lag I can introduce so that the system will still be stable. So that is what we are going to ask now. So basically now it means that so again it comes down to the Barkhaussen's condition. So we are interested in the gain of 1, right. So whenever the gain becomes greater than or equal to 1, that is when we are going to bother about the stability things. So now or in we say gain is 1 or we say 0 dB, right. So gain of 1 in multiplication becomes 0 dB when you take the logarithm, 20 log 1 is 0. So when we consider this 0 dB line. So this 0 dB line, so this is when it intersects the 0 dB line. So I just mark this down here. So this is the phase. So now this phase, okay, if I make a mistake of say this much phase lag, okay, if I can introduce this much phase lag to make the system unstable, the condition is at this particular value of gain equal to 1, I should have a minus 180 degree phase shift. So but now with this approximate model I am not getting minus 180 degree phase shift at this particular gain. So the system is stable, but for if I introduce what phase lag, will this system go unstable. So basically if I shift this down by something like this, okay, then at this point it becomes unstable, it becomes oscillatory, right, because now the critical frequency has changed here, and at the critical frequency this becomes like equal to gain becomes equal to 1, and so it starts oscillating. So there is what is the phase lag that we can add to the system to make the system oscillatory, or what is the phase lag that the system can withstand without becoming unstable. That is what we are going to ask this is. So what is the value of this? Basically this is the value. So this turns out to be around 76 degrees. So this is what the MATLAB gives. So this is 76 degrees, right. So minus 180 degree and minus 90. So if you made a mistake in modeling, or if you introduce some other component which is going to introduce a phase lag without changing the amplitude, etc., then if you introduce a phase lag of minus 70 degrees, 76 degrees, only then the system will become unstable. So I can make a mistake of say 10 degree phase lag, but system will still be stable, or when system is operating it can go like it can go to some other operating point, and then at that operating point if you find the system's model will be something different, because we take essentially what we do, we take a nonlinear system and then we linearize it. So at different operating point it will be different systems. So basically what we can say, we can accommodate of 76 degrees. 76 degrees will be the phase lag that I have to add to make the system unstable. So that is what is called the phase margin. So what is the phase I have to add, okay, to make the system unstable. So that is what is called the phase margin. So to summarize everything, fix the phase plot, ask the question like at minus 180 degrees, why minus 180 degree? Because with the negative sign in the feedback loop it becomes minus 180 degree plus this minus 180 degree, so minus 360, so multiples of 2 pi. So with this so at the minus 180 degree whatever is the angular frequency, that frequency is called the critical frequency. That is the first point we observe. Then we ask the question, like what is the gain at this particular critical frequency, and if the gain is say less than 1, then the system is stable. Then we do not stop the question there, we ask like, okay, what is the gain we have to multiply to make the system unstable. So that is giving us the bandwidth of, okay, we can multiply this much gain so that the system will be still stable. So that we got as 1.9. So that is the ultimate, and that is nothing but the gain margin. So that is 1.9 is nothing but 5.58 in decibels. So 5.58 decibels. So that is the gain margin thing. And now we fix the gain plot, and then we ask the question like, what is the phase lag I have to introduce so that the system goes unstable. So that is nothing but this given by at 0 dB, because like Barkhausen says like at equal to 1, right, the gain should be equal to 1. So at 1 when it becomes, what should I do to shift this to become like minus 180 degree. So what is the phase lag I have to introduce to make make this particular phase as minus 180 degree at that particular value when gain becomes equal to 1. So that is called the phase margin. So till what phase lag can I introduce so that still system will still remain stable, what is the maximum phase lag I have to introduce so the system will still remain stable. So that is called the phase margin. So that is nothing but 76 degrees here, and as you can clearly see, a higher gain margin and a higher phase margin will tell me that my I am safe, because I can multiply by a big number, I am still safe, I am still stable. I can introduce a big phase lag, I am still stable. But a smaller gain margin will mean that, for example, if I have a gain margin of say very less value, say I have a gain margin of say 0.001 dB or something like that, and it means that even a small mistake in modeling or even a small change in the gain of a system is going to push it to the instability. So a higher gain margin and higher phase margin is going to tell us we are the stability, from the stability point of view we are safe. A smaller gain margin and phase margin is not desirable, because which means that a small error in the modeling or a small change in the system parameters is going to cause a problem, is going to push the system to the unstable. And one more point you can think, it's not only about error in modeling, it's also about say some system parameters are not constant, basically they change with respect to time. For example, if you take the valve and all, it's moving continuously with respect to time, so all the time constant, everything is going to change. So in the real time everything is going to be changing with respect to time. So and this concept of like bandwidth, how much gain I have bandwidth and how much phase I have bandwidth, that is an important notion, not the exact Kp value, etc. So this is the concept of gain margin and phase margin. So maybe you can use this command of in MATLAB you can use margins. Basically in MATLAB you can use this command margins. You can give a transfer function, you can give a transfer function here, and then it is going to display this diagram, and you can basically play with this and then give a different transfer function and then see what it happens. So and remember, this whatever we use to find this is nothing but the we plot the Bode plot of an open loop system, okay, for the open loop system, because remember again we took this is Bode plot is going to give the magnitude of g of j omega and then the angle introduced by g of j omega when this system is g of s. So basically we are plotting for a open loop, and then we are saying okay, in the open loop if the phase lag is minus 180 degree and if the gain is amplitude of the gain is equal to 1, etc., then what happens. So for Bode plot we use the open loop transfer function, okay, and for this margin analysis also we use the open loop transfer function. That's something you have to remember. So it's not the closed loop transfer function we are using it here. Then I said okay, this method is not foolproof, it can fail, okay. So we will see some examples that clearly shows that this method is not going to work all the time. So that's what we will see now. So you take the transfer function 10 s plus 1 the whole square by s cube. So this is the open loop transfer function again, and then you plot the Bode diagram, and then you see like it says the gain margin is minus 180 degrees. So it means that we are already greater than gain is greater than 1. So 0 dB is the line when the gain is 1, and this is the critical frequency. Critical frequency is when we have minus 180 degree phase shift. So basically at this critical frequency the gain is going to be greater than or equal to 1. So by Barkhaussen's condition basically it means that the system should be oscillating, right? But let us see what happens. If you give a step input, system is not oscillating, it actually goes and settles here. So this method is not foolproof. This method is actually will fail in certain special cases, or but this is still working for a lot of. So what is the exact problem here? If you can see here, after this there are certain, another example that I can show you, but most of the times, most of the systems this works fine, this gain margin and phase margin concept works fine, but not all the time. So here you can see still its gain is greater than 1, the dB is gain margin is a negative number, which means that it is unstable, but you can see the system is stable here. So another example is like if you take g of s equal to minus 5, then what happens is basically the magnitude of g of j omega is equal to minus 5 for all the angle, and then the angle of minus g of j omega is nothing but minus 180 degree, right, because minus sign contributes to the minus 180 degree phase lag. So basically this means that the modulus is positive always, so modulus is 5, and this also again kind of pushes us to intuitively feel okay, this system is going to be unstable. But if you can write the closed loop transfer function with g of s by 1 plus g of s, what happens? It's nothing but minus 5 by minus 4 is nothing but 1.25. So this is a stable. In the, if you give a step input, the output is going to be 1.25 times of the input. That's what it's a stable system. So this is having some problem. So this gain margin and phase margin thing and Borel diagrams, all these things help us to understand intuitively that what exactly happens, why these things, why it can go unstable, but it's not always true. Sometimes it fails. Okay, that's something that you have to keep in mind. So now what we do, we go to the next concept called Nyquist stability criteria, which we will do it in a separate lecture. So that even in the lectures by professor, he has explained the Nyquist stability in a detailed manner. So we will run through some examples of Nyquist stability, and then we will see whether it can answer all these questions of stability, and whether it can handle all these problems that are faced by the body part, etc. So that's what we are planning for the next lecture. Thank you. And I also request you to play with, you take some transfer function and then you play with it, you draw the Borel diagram of it, and then you use MATLAB to find gain margin, phase margin, you do the root locus of it, you solve the problem by creating closed loop transfer function and then seeing the poles of the closed loop transfer function. So you play around all these things. All these three techniques should have the same answer, so that the answer should not change based on the technique you follow. So and then you try it out yourself, and you will actually start enjoying all these things. So that's what I ask you to do. It's a small request, and then thank you.